The darkness off Guadalcanal was absolute on the night of November 30th, 1942, as Commander Takeo Shibata stood on the bridge of the destroyer Takanami, watching his formation of 8 ships cut through the black water at 28 knots. No moon. No stars. Perfect conditions for the Tokyo Express run that had kept Japanese forces supplied through months of brutal fighting. His radar technician hunched over the Type 13 air search set, its greenish glow providing the only illumination in the darkened bridge, searching for American aircraft that never materialized. The first salvo arrived without warning. 5-inch shells bracketed Takanami at 0116 hours, their explosions turning night into day for brief, terrible seconds. Shibata's binoculars swept the darkness, searching for muzzle flashes that would reveal the enemy's position. Nothing. The Americans were firing from complete invisibility, their guns speaking from a void that Japanese lookouts, trained for years in night vision techniques, could not penetrate. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. American destroyers bearing 090, the lookout finally screamed, but by then 3 more salvos had found their mark. The heavy cruiser Northampton had opened fire at 14,000 yards, her radar-directed guns hitting targets her crew could not see with their eyes. Shibata watched in professional horror as the destroyer Takanami took a direct hit to her forward magazine, the explosion breaking her keel and dropping her into the sea within 2 minutes. Through his binoculars, Shibata finally spotted the American formation, 5 Fletcher-class destroyers in perfect line ahead, their distinctive flush deck profiles barely visible against the darker mass of Salvo Island. But they had seen his ships long before Japanese lookouts spotted them. The mathematics of this new warfare were brutally simple. American radar detection range exceeded Japanese visual detection by a factor of 3 to 1, even on the clearest nights. Takanami survived the engagement, limping back to Rabaul with 43 dead and her forward boiler room flooded. As damage control teams fought to keep her afloat, Shibata composed his after-action report in the captain's cabin, the words forming a conclusion that would reshape his career and, ultimately, his understanding of modern naval warfare. Enemy destroyers demonstrated detection capability, far exceeding our visual search methods. Engagement commenced at ranges impossible for optical targeting. Recommend immediate investigation of American radar technology and implementation of equivalent systems. The report reached Tokyo 3 days later, landing on the desk of Vice Admiral Isoroku Yamamoto's technical staff as part of a growing file, documenting the catastrophic toll that American radar was taking on Japanese naval operations. In the 6 months since Midway, Japanese destroyers had lost 37 separate engagements to radar-equipped American forces, suffering losses that were bleeding the Imperial Navy of irreplaceable ships and, more critically, irreplaceable crews. On December 8, 1942, exactly 1 year after Pearl Harbor, Shibata received orders transferring him from sea duty to the Naval Technical Bureau in Tokyo. His new assignment carried a priority classification that superseded all other naval construction projects: study American destroyer technology, determine how they achieved such overwhelming tactical advantage, design Japanese equivalents capable of matching American performance. Most critically, discover how the Americans had turned radar from a theoretical curiosity into a weapon system that was systematically destroying Japanese naval superiority in night combat, the very foundation upon which decades of training and doctrine had been built. Shibata departed Rabaul on a transport aircraft, carrying with him a briefcase containing every scrap of intelligence the Navy had collected on American destroyer radar systems. The file was disturbingly thin, consisting mostly of pilot reports describing antenna arrays atop American bridges and technical assessments, speculating about operating frequencies and detection ranges. What the file did not contain was any actual hardware, any detailed schematics, or any clear understanding of how the Americans had solved problems that Japanese radar engineers insisted were unsolvable given current technology. The answers, he would discover, lay in an abandoned dry dock in Surabaya, where an American destroyer sat waiting to reveal secrets that would ultimately prove more demoralizing than any battlefield defeat. Commander Shibata's office in the Naval Technical Bureau occupied the third floor of a reinforced concrete building in Tsukiji, its windows overlooking Tokyo Bay, where construction cranes marked the positions of two Yugumo-class destroyers under final assembly. On his desk lay 3 folders that defined the scope of Japan's challenge, their contents representing 9 months of intelligence gathering, prisoner interrogation, and technical analysis. The first folder contained specifications for the Fletcher-class destroyer, assembled from observation reports, captured documents, and measurements taken from aerial reconnaissance photographs. The numbers told a story of American industrial capability that bordered on the incomprehensible. 175 ships ordered. First vessel, USS Fletcher, commissioned June 30th, 1942. By January 1943, 28 already in service. Projected completion of entire class, 24 months. Shibata laid out the technical comparison on his drafting table, the specifications revealing both similarities and critical differences. Fletcher class, 376 feet length. Overall, beam of 39 feet 8 inches, 2,050 tons, standard displacement. 5 single-mounted 5-inch 38 caliber dual-purpose guns, 10 21-inch torpedo tubes in 2 quintuple mounts. Maximum speed, 37 knots from 60,000 shaft horsepower. Japan's Yugumo class, by comparison, measured 388 feet length, beam of 35 feet 5 inches, 2,070 tons standard displacement. 6 5-inch 50 caliber guns in 3 twin turrets, 8 24-inch Type 93 long lance torpedoes. Maximum speed, 35 knots from 52,000 shaft horsepower. On paper, the ships appeared roughly equivalent. In practice, the Americans were building them at a rate that made comparison meaningless. The second folder documented Japan's destroyer production. 18 Yugumo-class vessels ordered in 1941, with projected completion dates extending into 1945. Current completion. Rate, 2 per year. American completion rate for the Fletcher program, 6 per month across multiple shipyards. But the third folder contained information that transformed Shibata's assignment from analysis to opportunity. On February 22, 1942, the American destroyer USS Stuart had been scuttled in a floating dry dock at Surabaya to prevent her capture as Japanese forces advanced through Java. In February 1943, Japanese salvage teams had refloated both the dry dock and the destroyer, finding her remarkably intact despite a year underwater and the demolition charges her crew had set. Stuart was not a Fletcher-class vessel. She was a Clemson-class 4-stacker from 1920, displacing only 1,100 tons with 4 4-inch guns and 12 torpedo tubes. By 1943 standards, she was obsolete, her riveted hull and coal-fired boilers representing technology from the previous war. But Stuart had something invaluable. She had been fitted during a 1941 refit with mounting brackets for American radar systems, even though the actual radar sets had been removed before her abandonment. More importantly, her electrical systems, fire control wiring, and bridge layout reflected American integration philosophy for radar operations. She was a working example of how the U.S. Navy thought about destroyer radar deployment, preserved in steel and copper wire. Shibata boarded a transport to Surabaya on March 15, 1943, accompanied by a team of 6 engineers from Japan Radio Company. The destroyer sat in repair facility number 102, her hull repainted in Japanese grey, her 4 distinctive funnels marking her as unmistakably American despite the rising sun flag painted on her superstructure. Lieutenant Fukui Shizuo, the constructor overseeing her restoration, met Shibata at the dock with a folder of damage assessments and repair schedules. The destroyer could be made operational within 6 months, he explained, but more importantly, she could serve as a test platform for Japanese radar systems, allowing direct comparison with American integration methods. As Shibata climbed aboard and made his way to the bridge, he noticed details that separated American construction philosophy from Japanese practice. Standardized electrical connectors, color-coded wiring harnesses, inspection plates at regular intervals, equipment layouts designed for rapid replacement rather than permanent installation. Everything suggested a design philosophy that prioritized maintenance and repair by ordinary sailors rather than specialized technicians. The radar mounting positions told the most important story. American SG surface search radar belonged on the foremast, positioned for maximum horizon visibility. Fire control radar integrated with the Mark 37 director, providing targeting data directly to the gun mounts. The wiring runs showed how radar information flowed to a centralized combat information center, a concept that Japanese destroyers lacked entirely. Standing on Stewart's Bridge, looking at empty radar mounts that once held equipment giving American destroyers overwhelming advantage, Shibata understood the true scope of his mission. Japan didn't just need to build radar sets. They needed to replicate an entire system of naval warfare that integrated technology, training, and tactical doctrine in ways that Japanese military culture had never attempted. The question was whether such replication was even possible. Frank Kowalski ran lathe number 7 on the third shift at Springfield Armory, the overnight crew that kept production running while engineers slept. He'd been machining M1 Garand bolts since 1941, 40 bolts per shift, 8 hours of cutting steel to tolerances measured in 10,000ths of an inch. He was 42 years old, had a 10th grade education, and understood metal the way career engineers understood blueprints. Before Springfield, he'd worked 12 years at a paper mill in Vermont, maintaining machinery in an unheated building where winter temperatures regularly hit 20 below zero. He'd learned what engineers didn't teach in textbooks. Cold metal behaved differently than warm metal, and precision measurements made at room temperature became fiction in extreme cold. When the engineering team's memos started circulating in August about the Attu failures, Kowalski read them during his lunch break. The proposed solutions made sense on paper. Better lubricants, tighter tolerances, matched thermal expansion, all approaches that treated the problem like a precision engineering challenge. He saw it differently. The third week of August, he approached the shift supervisor with a request that sounded like professional suicide. He wanted permission to machine a bolt with deliberately loose tolerances. Not precision work, but sloppy work. Clearances of 8 to 10 10,000ths instead of the specification's 3 10,000ths. The supervisor thought he was joking. "You want to make parts that'll fail inspection?" "I want to make parts that'll work in Alaska," Kowalski said. "Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us." Now, back to the story. He explained his reasoning over coffee that had been sitting on the hot plate since 6 p.m. At room temperature, 3 10,000ths clearance was perfect. The bolt cycled smoothly, no excess play, no rattling. But at 30 below zero, metal contracted. The bolt body shrank. The firing pin channel shrank. That perfect fit became an interference fit. Parts that should slide locked solid. The solution wasn't better precision. It was worse precision, deliberately. Build in extra clearance at room temperature, so when cold made everything tighten up, there'd still be enough space for the mechanism to function. The supervisor, who'd spent 28 years on the shop and floor and understood the difference between what engineers specified and what actually worked, gave him permission to try. Off the clock, using his own time, with explicit understanding that if anyone in engineering found out, Kowalski would claim he'd screwed up the measurements. 3 nights later, working after his regular shift ended, Kowalski machined a bolt assembly with specifications that would have gotten him fired during normal production. The firing pin channel measured 9 10,000ths clearance instead of 3. The cam surfaces had an extra 5 10,000ths play. The locking lugs had clearances that violated interchangeability standards. He assembled the bolt at 2 a.m. with only the night janitor as witness, fitted it to a receiver, and dry-fired it 300 times. At room temperature, it felt loose compared to a standard bolt. The firing pin rattled slightly when he shook it. Quality control would have rejected it immediately, but Kowalski had spent 12 years fixing paper mill machinery at 20 below zero. He'd learned that equipment built tight for summer needed to be built loose for winter. Tolerances that seemed sloppy in warm conditions became perfect in cold, the reverse of what precision manufacturing taught. He wrote a one-page memo describing his modification and left it on the engineering department supervisor's desk on Friday morning, September 3rd. The memo disappeared into the stack of proposed solutions that arrived daily from machinists, soldiers, and concerned citizens who all had ideas about fixing the M1. 2 weeks passed. Kowalski received no response. His bolt sat in his locker, unofficially manufactured, technically violating specifications, and completely outside the formal testing program. Then, in late September, a second shift inspector named Margaret Torres found the memo while filing paperwork. She'd read the engineering reports about cold weather failures. She'd seen the test results showing that every precision solution had failed, and she'd worked at Springfield long enough to know that sometimes the machine operators understood things that the engineers missed. She brought the memo to John Garand himself, who'd been personally reviewing every proposed modification for 3 months. Garand read it, reread it, and recognized something the engineering team had missed. They'd been trying to make the rifle more precise. This machinist was proposing to make it less precise in exactly the right way. On October 1st, 1943, Garand requested that Kowalski's modified bolt be included in the next round of cold weather testing. Not as a serious candidate, the chief engineer noted in his log, but as an experimental control to verify that loose tolerances caused the problems they expected. They thought it would fail spectacularly. They were preparing to use its failure as proof that precision was necessary. They didn't know they were about to discover that sometimes the solution to an engineering problem is to engineer it worse. Springfield Armory's cold weather test facility was a converted meat locker, 14 feet by 20 feet, with a refrigeration system capable of reaching 50 degrees below 0 Fahrenheit. By October, it had become the most important room in the entire arsenal. Every proposed solution to the ATU failures ran through this chamber. The test protocol was straightforward. Load 8 rounds, fire 8 rounds, reload, repeat. Continue until either 200 rounds were successfully fired or until the rifle experienced 3 consecutive malfunctions. Ambient temperature, -30 degrees Fahrenheit. No artificial heating. No special maintenance between firing strings. Conditions matching what soldiers faced in the Aleutians. Through September and early October, 17 different modifications were tested. Enhanced lubricants that supposedly remained fluid at -40. Redesigned firing pins with reduced mass. Modified bolt carriers with special surface treatments. Tighter tolerances supposedly eliminating moisture infiltration. Each modification represented hundreds of engineering hours and the collective expertise of men who'd spent careers perfecting the M1 Garand. Every single one failed at -30 degrees. The enhanced lubricants worked until approximately round 40, when powder residue mixed with oil and created a paste that bound the firing pin. The lightened firing pins showed insufficient energy to reliably detonate primers in cold conditions. The surface treatments helped for perhaps 20 rounds before frost buildup caused binding. The tighter tolerances made the problem worse, exactly as Kowalski had predicted. By October 14th, the testing program was desperate. John Garand, reviewing failure reports in his office, was facing the possibility that the M1 couldn't be modified for Arctic warfare. That American soldiers would need to fight with bolt actions in cold weather, surrendering the 3-to-1 firepower advantage that the Garand provided. The test schedule for October 15th included 3 rifles. 2 represented the engineering team's latest modifications, a bolt with specially hardened surfaces and a firing pin with modified spring tension. The third rifle, listed at the bottom of the test sheet with a notation reading Machinist Proposal, Loose Tolerances, was Kowalski's bolt. The test engineer, a captain named Robert Herschel who'd overseen 53 failed tests, loaded Kowalski's rifle last. He expected it to fail immediately. The bolt rattled. The firing pin had visible play. At room temperature, before entering the cold chamber, it felt wrong compared to a standard M1. Imprecise. Sloppy. Minus 30 degrees Fahrenheit. 8 rounds loaded. First trigger pull. The rifle fired. 8 rounds. Smooth cycling. No malfunctions. Reload. 8 more rounds. Perfect function. Another reload. The rifle that shouldn't work kept working. 24 rounds. 40 rounds. 80 rounds. Herschel stopped at 100 rounds, removed the rifle from the chamber, and inspected the bolt. It was cold enough to stick to bare skin. Ice crystals had formed around the gas port, but the mechanism moved freely. The firing pin channel, with its deliberately excessive clearance, had enough space that minor frost buildup didn't prevent operation. He returned the rifle to the chamber and continued testing. 120 rounds, 160, 180. At round 193, the rifle experienced its first malfunction, a failure to eject caused by a defective cartridge, not a mechanical failure. Herschel cleared it and continued. 200 rounds total. 1 malfunction unrelated to the cold weather modification. The 2 precision-engineered modifications, tested simultaneously, failed at 37 and 42 rounds respectively. Both experienced firing pin binding, both were removed from the chamber as failures. Kowalski's sloppy bolt had fired 200 rounds at minus 30 degrees with 99.5% reliability. Herschel ran the test again the next day with a fresh rifle using Kowalski's tolerance specifications. This time at minus 40 degrees Fahrenheit, colder than Attu, matching the worst conditions American troops might face. 200 rounds. 0 malfunctions attributable to cold. The engineering team assembled on October 18th to review the results. 15 engineers, including John Garand, examined data that contradicted their training. The precision solution had failed. The imprecise solution had succeeded. The bolt that would have been rejected by quality control in peacetime had proven more reliable in extreme cold than any precisely manufactured alternative. The explanation, once they accepted it, was straightforward. At minus 30 degrees, the excessive clearances of 9/10,000ths became optimal clearances of approximately 4/10,000ths after thermal contraction. The parts that seemed loose at room temperature achieved perfect fit at operational temperature. Precision engineering had been designing for the wrong temperature. Kowalski had designed for the temperature where soldiers actually fired the rifle. On October 22, 1943, Springfield Armory issued Technical Bulletin Number 47, Cold Weather Modification of M1 Rifle, Bolt Assembly. The bulletin specified tolerance ranges that were, by peacetime standards, unacceptably loose. Quality control inspectors received new guidelines. Parts that would have failed inspection a month earlier were now the standard. Frank Kowalski received a commendation and a $50 war bond. More significantly, he received reassignment to the day shift as a technical consultant. The machinist who'd been told his idea was stupid was now teaching engineers how to build weapons that actually worked. The challenge, now, was manufacturing 50,000 modified bolts while convincing a precision-obsessed production system to accept parts that looked wrong but worked right. The irony that would haunt Commander Shibata's investigation began in 1937, 4 years before Pearl Harbor, in a laboratory at Japan Radio Company, where engineer Yoji Ito was developing what would later be recognized as one of the war's most critical technologies. Working under Professor Kinjiro Okabe at Osaka University, Ito had created an 8-segment cavity magnetron capable of producing 500 watts of power at 10 centimeters wavelength. The British wouldn't produce their comparable design until February 1940, giving Japan a 3-year head start in the technology that would define modern radar warfare. Shibata learned this history on June 8, 1943, standing in the JRC factory in Kawasaki, as Chief Engineer Nakamura Hideki explained how Japan had pioneered microwave radar technology, only to watch the Allies transform that same technology into weapons that were systematically destroying Japanese naval forces. The factory floor stretched 200 meters, filled with workbenches where technicians hand-assembled Type 22 radar sets under conditions that made mass production impossible. "We call it the chrysanthemum magnetron," Nakamura explained, holding up the 8-cavity copper block that formed the heart of Japan's naval radar program. Ito-san designed it in 1939, before anyone else achieved stable microwave generation. The British Randall and Boot magnetron that everyone credits as revolutionary? We had equivalent technology 18 months earlier. The magnetron in Nakamura's hand represented the pinnacle of Japanese precision engineering. Each cavity had been individually machined to tolerances of 5 microns, the copper block polished to mirror finish, the ceramic insulators hand-fitted by craftsmen with 20 years' experience. It was a masterpiece. It was also useless for winning a war. "Production output?" Shibata asked, watching technicians at the assembly benches. Nakamura's expression darkened. "We completed 60 Type 22 sets between September 1942 and March of this year. Of those 60, approximately 6 achieved specifications that met operational requirements. The others suffered from frequency drift, power output variations, or complete failure after fewer than 10 operating hours." The mathematics were devastating. A 10% success rate meant that Japan's most advanced radar program was producing less than 1 usable set per month. Meanwhile, American factories were churning out SG surface search radars at rates Shibata had difficulty believing until he saw the intelligence estimates. Over 2,000 sets completed by spring 1943, equipping everything from battleships to destroyer escorts. The factory tour revealed why Japanese production rates would never match American output. Each Type 22 magnetron required 16 hours of individual fitting and tuning by a master technician. The waveguide assemblies used hand-soldered connections rather than standardized flanges. Crystal detectors came in 17 different variations, each requiring calibration against the specific magnetron it would serve. The 40 vacuum tubes in each receiver were individually selected and matched for gain characteristics. "Show me an American radar set," Shibata requested. Nakamura led him to a corner workbench where engineers had disassembled a captured SG radar removed from a damaged destroyer at Guadalcanal. The contrast with Japanese equipment was immediately apparent. American magnetrons used a simpler resonant cavity design that sacrificed theoretical peak performance for consistent reliability. Waveguide sections connected via standardized flanges that any shipyard machinist could fabricate. The receiver used just 23 tubes, all standard types available from multiple manufacturers. Color-coded wiring and numbered terminal strips meant that installation required no specialized knowledge. "This is inferior to our Type 22 inches every measurable specification," Nakamura said, his voice carrying professional disdain. "Lower peak power output, cruder frequency control, less precise bearing resolution. Any competent engineer can see that our design is technically superior. And yet they've installed 2,000 of these inferior sets on their ships," Shibata replied quietly, "while we've managed to produce 6 functional examples of our superior design. Technical excellence that cannot be manufactured is strategically worthless." The quality control problem extended beyond the magnetrons. Shibata watched as a technician spent 40 minutes adjusting a crystal detector, trying to achieve optimal sensitivity. The crystals themselves, silicon specimens grown in laboratory conditions and hand-selected for rectification, properties, varied wildly in performance. American radars used mass-produced crystal detectors that worked adequately in 95% of installations. Japanese crystals worked perfectly in 5% of installations, and failed completely in the others. The philosophical divide became clear as Shibata examined the production records. JRC engineers designed the Type 22 as a technical demonstration, proving that Japanese electronics could achieve performance specifications that equaled or exceeded Allied equipment. Every component represented the absolute pinnacle of what Japanese manufacturing could achieve given unlimited time and resources. The problem was that modern naval warfare didn't allow unlimited time, and Japan's resources were already stretched beyond sustainability. American engineers, by contrast, had designed the SG radar as a product rather than a prototype. Components were selected not for maximum theoretical performance, but for consistency, availability, and ease of manufacture. The entire system was engineered so that semi-skilled workers using standard machine tools could produce units that met minimum acceptable specifications every time. Where Japanese designs optimized for perfection, American designs optimized for adequacy at scale. Can we modify the Type 22 for mass production? Shibata asked, knowing the answer but needing to hear it stated explicitly. Nakamura shook his head. Fundamental redesign would be required, looser tolerances, simplified circuitry, standardized components. We would be accepting performance degradation in exchange for production capability. Perhaps 20% reduction in maximum range, slower bearing updates, less precise targeting data. Nakamura paused, choosing his words carefully. We would be building equipment inferior to what we know is possible, inferior to what our technical capability can achieve. Shibata looked out across the factory floor, where 6 master technicians were assembling 6 Type 22 radar sets that would take 6 months to complete. In those same 6 months, American factories would produce over 500 radar sets using workers who had learned their jobs in 6 weeks. The choice wasn't between Japanese technical excellence and American mass production. The choice was between beautiful equipment that didn't exist in sufficient quantities to matter, or adequate equipment that existed in overwhelming numbers. Japan, he realized, had already made its choice 4 years earlier, when engineers decided to optimize for perfection rather than practicality. Now they were watching American pragmatism systematically dismantle Japanese technical achievement through the brutal arithmetic of industrial warfare. The destroyer that Imperial Japanese Navy records listed as Patrol Boat No. 102 departed Surabaya Harbor on September 20, 1943, carrying equipment that represented Japan's attempt to match American radar capability. Commander Shibata watched from the bridge as the old 4-stacker worked up to 26 knots, her 3 functioning boilers pushing her through tropical waters toward the test range north of Java, where he would finally compare Japanese and American radar integration methods under operational conditions. 2 Type 22 radar sets had been installed aboard the former USS Stuart, positioned where American SG radars would normally mount. The forward set occupied a platform atop the bridge, its distinctive twin-horn antenna rotating at 5 revolutions per minute. The second set sat just aft of the No. 2 funnel, providing redundancy and allowing comparison of mounting positions. Installation had required 4 months of work by JRC engineers, custom fabricating mounting brackets and running over 2,000 meters of shielded cable through spaces never designed for such equipment. Lieutenant Mizutani Tamotsu, Stuart's new commanding officer, had spent 6 weeks training on radar operation at the Navy Technical School in Yokosuka. His radar operators, Petty Officers Yamamoto and Suzuki, represented the best candidates available, both having university education in electrical engineering. American radar operators, Shibata had learned from interrogation reports, received 3 weeks of training and typically possessed only high school education. The test protocol was simple. A Japanese destroyer, Yugumo, would operate at varying ranges from Stuart while both ships tracked each other using radar. Yugumo carried a Type 22 set that had been operational for 8 months, providing a baseline for comparison. The exercise would determine effective detection ranges, bearing accuracy, and operational reliability under conditions simulating combat operations. At 0800 hours, Yugumo departed her position 15 nautical miles northeast of Stewart and began closing at 20 knots. Shibata stood behind Yamamoto in the cramped space that Stewart's engineers had, designated the radar room, watching the Type 22's A-scope display as the operator adjusted sensitivity controls and tuned the receiver for optimal response. Contact, Yamamoto, announced at 0823 hours. The range indicator showed 28,000 meters, approximately 15 nautical miles. Shibata noted the time and range in his log, aware that captured American SG radars regularly detected destroyer-sized targets at 25 nautical miles under similar conditions. The Type 22 was already performing at half the range of equipment the Americans considered standard. The bearing accuracy test revealed more troubling problems. As Yugumo closed to 10 nautical miles, Yamamoto reported bearing updates every 30 seconds. The bearings varied by up to 3 degrees between successive reports, making accurate fire control solutions impossible without extensive averaging and calculation. American SG radar, according to technical assessments, maintained bearing accuracy within 1 degree at comparable ranges. At 0947 hours, 47 minutes into the exercise, the forward Type 22 set failed completely. Yamamoto reported loss of all returns, and investigation revealed that the magnetron had stopped oscillating. The engineering team dispatched to the radar platform discovered that vibration from the ship's engine had loosened a vacuum tube socket, interrupting the circuit that powered the magnetron's electromagnet. The repair required 12 minutes, and the attention of both JRC engineers who had sailed with Stewart specifically to handle such failures. American radar sets, Shibata knew from examining captured examples, used shock-mounted chassis and locked tube sockets precisely to prevent failures from shipboard vibration. Japanese engineering philosophy had focused on achieving maximum performance, assuming that installations would occur in laboratory-like conditions rather than aboard warships that shook continuously from machinery, vibration, and routine operations. The aft Type 22 set continued functioning, and the exercise proceeded through midday as Yugumo executed a series of tactical maneuvers designed to test tracking capability. The results documented a gulf between Japanese and American radar capability that extended far beyond simple detection range. American radar operators worked in combat information centers, dedicated spaces where multiple operators managed surface and air search radars, while plotting teams maintained running tracks of all contacts. Japanese destroyers had no equivalent facility. Radar operators worked in isolation, calling contacts to the bridge via voice tube, with no systematic method of correlating information or maintaining situational awareness. Shibata spent the afternoon in Stewart's chart room, attempting to plot Yugumo's movements based on radar reports. The exercise proved impossible. Bearing variations of 3 degrees at 10-mile range translated to position uncertainties of over half a mile. Range estimates varied by 800 meters between successive reports. Fire control solutions required 5 minutes of calculation by the gunnery officer, by which time the target had moved to a new position requiring fresh calculations. American destroyer tactics, intelligence reports indicated, relied on radar-directed torpedo attacks executed from ranges of 10,000 meters in complete darkness. Japanese long-lance torpedoes were technically superior to American Mark 15 torpedoes in every measurable characteristic: speed, range, warhead size, reliability. But what advantage did superior torpedoes provide when the weapons could not be aimed accurately because radar could not provide reliable fire control data? On September 23, after 3 days of testing that produced similar failures and frustrations, Shibata composed his assessment report in Stewart's cramped captain's cabin. The conclusion wrote itself. Japan had succeeded in creating radar sets that matched or exceeded American equipment in theoretical capability, but failed catastrophically in practical application. The Type 22 magnetron design represented cutting-edge microwave technology, The American SG magnetron was simpler, cruder, and less elegant, but American magnetrons worked reliably for hundreds of operating hours, while Japanese magnetrons required constant adjustment and frequent replacement. Japanese radar operators required university-level training to achieve marginal competence. American radar operators with high school education achieved operational proficiency in 3 weeks. Japanese radar sets required master technicians for maintenance. American radar sets could be serviced by ordinary electricians using standard tools. Most critically, American destroyers were built from the keel up to accommodate radar operations, with electrical capacity, wiring runs, and bridge layouts designed around combat information centers that integrated all sensor data into coherent tactical pictures. Japanese destroyers received radar as an afterthought, with equipment bolted onto structures never intended to carry such systems and operators working in isolation from other watch stations. "We are not attempting to copy American technology," Shibata wrote in his conclusion. "We are attempting to replicate American industrial philosophy, and we lack the cultural foundation to do so. Our engineers build equipment that represents the pinnacle of individual achievement. American engineers build systems that function reliably when operated by ordinary people under extraordinary circumstances. We optimize for excellence. They optimize for adequacy at scale, and adequacy at scale is winning the war." The report went to Tokyo by air courier on September 25, 1943. Shibata never received official response or acknowledgement that anyone in the Navy High Command had read his assessment. Ex-USS Stewart continued operating as patrol boat number 102, her Type 22 radar sets, failing regularly and requiring constant attention from specialized technicians who were desperately needed at factories producing equipment that didn't work properly. The numbers that arrived on Commander Shibata's desk in January 1944 told a story of industrial divergence so extreme that he initially suspected the intelligence estimates contained errors. According to reports compiled by the Navy General Staff's Analysis Section, American shipyards had completed 132 Fletcher-class destroyers by the end of 1943, with an additional 43 vessels in various stages of construction. Projected completion date for the entire 175-ship program, mid-1945. Japan's Yugumo-class program, initiated in 1941 with similar goals of creating a standardized fleet destroyer, had produced 11 completed vessels by January 1944. 7 more were under construction at yards in Yokosuka, Maizuru, and Sasebo, with completion dates extending into 1946 if current production rates continued. The arithmetic was devastating. American shipyards were delivering Fletcher-class destroyers at a rate of 6 per month, while Japanese yards struggled to complete 1 Yugumo every 8 weeks. The man-hour analysis revealed the fundamental problem. Each Fletcher-class destroyer required approximately 15,000 man-hours of labor from keel laying to commissioning, according to estimates derived from observed construction timelines and shipyard employment figures. Japanese destroyers consumed over 32,000 man-hours for equivalent work, more than twice the American requirement for ships of similar size and capability. The difference wasn't explained by Japanese inefficiency or inferior shipbuilding techniques. Japanese shipwrights and welders were among the world's most skilled, their craftsmanship evident in every centimeter of hull plating and structural member. The problem lay in design philosophy. American destroyers used standardized components fabricated in specialized facilities and shipped to assembly yards for installation. Japanese destroyers used custom-fitted components machined individually to match the specific characteristics of each hull. Shibata visited the Maizuru Naval Arsenal on February 14, 1944, observing the construction of destroyer Fujinami. The ship was 70% complete, her hull plated and her main machinery installed, but work had stalled for 3 weeks, waiting for custom-machined reduction gears that would mate her turbines to the propeller shafts. American destroyers used standardized reduction gears produced by Westinghouse or General Electric in quantities that allowed immediate replacement of damaged units. Japanese reduction gears were individually matched sets, each one unique to the specific turbines and shaft arrangement of the destroyer for which they were intended. By 1944, Japan's radar program symbolized its broader industrial collapse. Fewer than 300 Type 22 radar sets had been built, barely 90 operational, while the US Navy had produced over 3,000 SG radars. Japan's skilled labor crisis deepened as technicians were drafted and air raids destroyed key electronics factories. Aluminum shortages and loss of experienced workers crippled production. By mid-1944, students as young as 14 were assembling complex equipment they barely understood. Of 30 radar sets built that summer, only 4 passed initial tests. Commander Shibata's September 1944 report to the Navy Technical Bureau documented the crisis: 168 American Fletcher-class destroyers versus 14 Japanese Yagumo-class, 4,000 US. Radar sets versus 320 Japanese. His warning that Japan's destroyer forces would soon vanish strategically drew no response. Studying a captured American radar manual, Shibata saw the deeper issue. The US designed equipment for 19-year-old sailors, simple, modular, repairable in minutes. Japan's manuals demanded engineers, precision tools, and laboratory conditions. American destroyers used standardized components and mass production tolerances. Japanese systems pursued perfection through handcrafted parts requiring constant expert attention. This contrast reflected 2 national philosophies. Japan's tradition of master craftsmanship created technological masterpieces too delicate for wartime demands. America's industrial system prioritized functionality and reproducibility, producing thousands of good-enough weapons that could be maintained by ordinary men. Shibata's final 1944 report summarized the truth. We are building museum pieces while the Americans are building weapons. His analysis went unread. Japanese artisans continued producing a few exquisite radar sets per month as American factories turned out hundreds, each cycle widening the gap between technical artistry and industrial warfare, a difference not of quality, but of survival. On the night of the 25th of October 1944, at Surigao Strait, Rear Admiral Jesse Oldendorf's 6 battleships formed a deadly trap for Vice Admiral Shoji Nishimura's Southern Force. 39 destroyers and 28 PT boats, guided by radar, tracked the Japanese approach unseen. At 0300, USS Melvin detected Nishimura's ships at 36,000 yards and fired torpedoes, guided entirely by radar. One struck battleship Fuso, breaking her in half. Japanese destroyers carried advanced Type 22 radars, but their operators lacked the training, coordination, and doctrine to use them effectively. Information was reported slowly and in isolation, while American ships shared radar data across voice networks, forming a unified tactical picture. When Yamagumo's radar failed from vibration, she fought blind until torpedoes sank her minutes later. American fire control radars then enabled Oldendorf's battleships to cross the T, striking Japanese ships from over 20,000 yards. 2 Japanese battleships and 3 destroyers were destroyed. US losses were negligible. Commander Shibata's later analysis concluded Japan's destroyer forces were obsolete by 1943. Superior torpedoes and optics meant nothing against radar-guided fire control and coordination. The US won through integration and quantity, not perfection. Its simple, mass-produced radars turned night combat into a science Japan could no longer match. On the 29th of August 1945, Commander Takeo Shibata watched American engineers examine the Type 22 radar on the captured destroyer USS Stuart, now Japanese patrol boat number 102. The war was over, and the US Naval Technical Mission was cataloguing Japan's triumphs and failures. Lieutenant Commander Harold Watson praised Japan's magnetron design as ahead of its time, but noted that America had industrialized the idea. By war's end, Japan had built 300 Type 22 radars. The US had built over 10,000 SG sets. Watson's team found the Type 22 technically superior in precision and sensitivity, yet impractical. It required master craftsmen to build and engineers to maintain. Installation took months, repairs took weeks, and operators lacked the training to use it effectively. The American SG, by contrast, was mass-produced, easy to install, and maintainable by ordinary sailors. In their final discussion, Shibata concluded, "You designed weapons systems. We designed demonstrations. The nation that arms ordinary people with adequate weapons wins." Watson's report summarized Japan's defeat. Japan built 300 excellent radars. America built 10,000 adequate ones. Adequacy at scale defeated excellence in small quantities. Shibata later wrote, "Modern war is won not by better weapons, but by sufficient weapons built in overwhelming numbers." Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.